Hello all, welcome back. We're going through more of Chapter 7a. So this next topic in Chapter 7a, deducing N and L from a subshell label. So we're going to get a lot more into electrons and how they orbit around the nucleus. Then we'll talk about what the heck N and L mean in terms of electrons. So we looked at previously Bohr's model of the atom. We saw the nucleus here that contains protons and neutrons. Again, now we're talking a lot more about how the electrons are oriented around the nucleus. So here's our nucleus in the middle. Then N equal 1 is the first energy level. N equal 2 is the second energy level. N equal 3, the third energy level. And these go on, N equal 4, N equal 5, etc. These all describe energy levels that electrons can exist in. And electrons can only have specified, discrete, which then comes to this term of quantized energy values. That means these electrons can only exist at these set discrete energy levels around the nucleus. That's what's meant by quantized or specific, discrete, set, quantized energy levels or energy values, where each energy level has an associated energy value. In part 1 of Chapter 7a, we talked about an electron being emitted from an atom when some light wavelength hits an atom. So if a wavelength interacts with an atom, an electron can be ejected from the atom. We're putting in some energy, some electron is put out. This still comes back to the idea that energy can neither be created nor destroyed. So if we input energy, that energy has to go somewhere. It's emitted in the form of an electron. Now here, we can also have an electron instead go from N equal 3 to N equal 2 energy levels. N equal 3 is a higher energy level than N equal 2. When an electron goes from N equal 3, it's at a higher energy value, then it goes down to N equal 2, that's a lower energy value. That means there is excess energy that needs to go somewhere. It can't just disappear, so the energy needs to go somewhere. We see that energy in the form of light or in the form of a wave or a photon being emitted from the atom, where the atom contains that nucleus and all of these surrounding electrons around that nucleus. So when we input energy, an electron is emitted, but when an electron goes from a higher energy level to a lower energy level, then actually energy is emitted. This energy is emitted in the form of a photon or a wave, because again, we have the electron at a higher energy level, it goes to a lower energy level. We have a temporary excess of energy. That has to go somewhere. That is in the form now of an emitted wave, where this wave is the energy, the excess energy. So the energy of this photon or wave is equal to the energy difference between the two N levels in the atom. So the energy difference between this N equal 3 energy level to the energy of N equal 2, that difference is also the energy of this emitted photon. And the emitted photon can go on the same trajectory of a wave like we saw in part 1. So light is emitted as an electron moves from one energy level to a lower energy level. It can be from N equal 3 to N equal 2, could be from N equal 4 to N equal 1, so higher energy level, and here's a relatively lower energy level. What we're getting at is the complexity of the electron arrangement around the nucleus. If an atom is exposed to light, it can emit or eject an electron, but if an electron goes down in energy level, then now energy is emitted from the atom. because we can't have energy just disappear. It has to go somewhere, either in the form of an electron being emitted or in the form of a photon being emitted from that atom. Let's talk more about what it means for this to be quantized. Remember, this electron can be at n equal 1, n equal 2, n equal 3, n equal 4, etc. Because the electron is quantized, that means it cannot be found just hanging out in the middle between two energy levels. Another way to picture this quantized energy is we have steps like a staircase. This red sphere can be at this step or this energy level, and it can go down an energy level or down a step. We're not going to see this red sphere sort of in the middle between two steps. That sphere has to be at a set step. It is quantized. So energy levels of the atom are quantized, similar to how these steps are quantized. This is a set specific step or energy level. So is this one, this one, this one, this one. Just like the spheres have to be at these set energy levels, the electrons do as well. They have to be at n equal 1, n equal 2, n equal 3, etc. They are quantized. Those electrons are not going to be found somewhere in the middle in between two energy levels. So this staircase analogy is a nice one to think about to connect how we can picture electrons around the nucleus. They're quantized, they're at set energy levels around the nucleus. Like we saw in 7.8 part 1, we can describe energy as Planck's constant times the frequency. So we could, in theory, describe the energy because we know Planck's constant, but we'd also have to know the frequency of an electron. Well, how can an electron have a certain frequency? What is frequency again? Let's say we have some wave that's propagating. Let's say we're standing right here, so that's our eye, looking at this point right here. Remember, frequency is how many times the wave passes through a set point in units of per second or hertz. If we stood right here and the wave passed through 5 times, if the trough of the wave specifically, we have to think of the same point each time, if it passed through this point 5 times, then that's 5 cycles per second, or 5 hertz, or 5 1/seconds. So that's our idea of frequency. We can take a wave and describe the frequency. How do electrons have a frequency? How do electrons have a wave? Well, if we have this nucleus and let's say this is energy level 3. We also have, more energy levels below here, n equal 1, n equal 2, etc. In each energy level, we're going to have an integer number of wavelengths that can fit around the circumference of the atom. So the circumference of each energy level is a very specific set distance to allow for complete wavelengths to pass along. We count wavelengths as trough to trough to trough, or peak to peak to peak to peak. We're not going to have some energy level have a circumference where we have something like this happen for an electron. The electron has to be able to complete full wavelengths around the nucleus within each specific quantized energy level. So electrons can also act as both particles and waves, just like we saw for electromagnetic radiation. We talked about this idea of light or electromagnetic radiation having both wave and particle duality. So there's a dual nature to electromagnetic radiation. There is a dual nature to electrons as well. This was the work of de Broglie. This built on, of course, work of other scientists. Just to point out here, this was in 1924, so not really that long ago. So the circumference of an orbit must be an integral number of wavelengths of the electron. So this is at n equal 3. What we can also say about the electrons is this circumference of n equal 2 has to be the same. We have to have an integral number of wavelengths that that electron can pass through. Same with n equal 1, n equal 4. Any of our energy levels have to have that set circumference. If you go on to take physical chemistry, you'll hear a lot more about Schrödinger. If you've heard of Schrödinger's cat, you can look into that. It's this quantum idea that the cat can be both simultaneously alive and dead. There's some cool YouTube videos out there on Schrödinger's cat. We're not going to go too in depth with the quantum aspect of general chemistry, but in the year 1926, Schrödinger wrote an equation that described both the particle and wave nature of electrons as part of this wave function. This describes the energy of the electron and the probability of finding an electron in some set volume of space around the nucleus. What is the probability, for example, of finding an electron within this circular volume? What is the energy of the electrons? So Schrödinger's wave function describes both the energy and the probability of finding an electron in a certain volume and the energy of that electron in that given volume. It gets more complicated if we have more than one electron that's around the nucleus. So the one element that has only one electron is hydrogen. It gets even more complicated if we have multi-electron elements. So essentially any other element aside from hydrogen, unless we had one of our lower atomic number elements that lost some electrons and that element only had one, that's another way we could potentially end up with fewer number of electrons, but we know hydrogen is the simplest element, at least atomically. What we're getting into here in Chapter 7a, Part 2, is all about these electrons and how they're oriented around this nucleus. There's a lot of modeling done to describe the location of electrons around the nucleus. We're going to touch on that now. I mentioned we would discuss what is N and what is L. Let's start with N. N is considered one of our spin quantum numbers. There are 4 spin quantum numbers in total: N, L, M sub L, and M sub S. These all attempt to describe, again, how electrons are oriented around a nucleus. Let's talk about N. So N is the first spin quantum number. N is the principal quantum number. It can be in amounts of 1, 2, 3, 4, etc. Notice that N cannot be 0. So N starts at 1, then in integer amounts, N 1, 2, 3, 4. Those are set values for N. This can go on. So 5, 6, 7, etc. N, our principal quantum number, describes the distance of an electron from the nucleus. N equal 1, we are closest to the nucleus. N equal 2, we are 1 energy level away from N equal 1. So 2 energy levels away from the nucleus. N equal 3, we are 3 energy levels away from the nucleus. Remember, electrons are in quantized energy levels. We're not going to find an electron between N equal 1 and N equal 2, only at these set energy levels. So N, our principal quantum number, first describes the distance of an electron from the nucleus. That's our first quantum number we're going through. We'll talk about what this S means here in Chapter 7. Right now, something to notice is that this 1, 2, and 3 out front, those are our numbers for N. So first spin quantum number we just talked about is N. Next, let's talk about L. L is the second spin quantum number. So we talked about N. What L describes, or what it's called, is the angular momentum quantum number. N was the principal. L is the angular momentum quantum number. The allowed values for L is that L can equal 0, 1, 2, 3, etc. So L can equal 0. An important restriction on the possible values for L is that it can be 0 up through n equals 1. And it's this angular momentum quantum number. What does that really mean? It describes the shape of the volume of the space that the electron occupies. So the shape of the volume. So L describes the shape. What does that mean? What does it mean that L can describe different shapes of the volume that contains electrons? Well, we'll see in just a bit that we can have these proposed shapes that the electrons could fall in. So some shape like this kind of looks like flower petals. We'll look at all the different shapes within chapter 7. So L describes the shape of the volume of space that the electron occupies. So this is sort of a 3D flower petal around the nucleus. We'll talk a lot more about this. This happens to be one of our P-shaped orbitals, is what I drew. Again, we'll talk a lot more about these. Let's give an example. Let's say n is equal to 1. We want to figure out the possible values for L. For L, it's going to be 0 up through the value of n minus 1. If we know our n, let's do 1 minus 1, that's 0. So when n equals 1, the only possible value for L is 0. If n is equal to 2, then n equals 2. 2 minus 1 is 1. That means our possible values for L is 0 up through n minus 1, which is 1. So for n equal 2, L can be either 0 or 1. N equal 3, we do 3 minus 1, that's 2. The possible values for L, 0, 1, and 2. So starting at 0, then in integer amounts can go up through the value of n minus 1. When L is equal to 0, this describes an S-shaped orbital, L equal to 1, a P-shaped orbital, L equal to 2, D, L equal to 3, F. To start to get you initiated with this, an S-shaped orbital just looks like a sphere. P-shaped orbitals, they look like these flower petals in the Y plane, X plane, and in the Z plane. For p orbitals, for example, then, this describes the idea that the electron will be found in these shapes of the flower petals. For an s orbital, that's a sphere, the electrons can be found somewhere within that sphere. D-shaped orbitals get even more complex, so do F. Again, we're describing the possible location of electrons around the nucleus. So we talked about N, we talked about L. Let's talk about M sub L. This is our magnetic quantum number. This describes the orientation of the orbital in space. So how the actual orbital is located in space, how it's oriented in space. For example, with the p orbitals, this set of p orbitals is situated on the y-axis. We'll practice doing a lot more with how we figure out 0, 1, 2, 3 for L. We know that based on the value for n. And again, we'll go into more about these orbitals. Let's say we have a value for n and L. How do we find the possible values for M sub L, the orientation of the orbital in space? The reason these spin quantum numbers were developed is to describe the complexity of the electrons around the nucleus, the location of the electrons around the nucleus. This is one way we can picture these electrons or describe these electrons around the nucleus is using these spin quantum numbers. So for M sub L, our magnetic quantum number, the reason it's considered a magnetic quantum number, we know electrons are negatively charged. We know we can have some magnet that has polarity to it, where it has a positive end and a negative end. So that helps describe the orientation of the electrons. That's where we get this name of magnetic quantum number. For a given value for L, So if we know our L value, our possible values for M sub L is negative L through 0, so including 0, up through positive L. Just to reiterate again, N itself, the principal quantum number, cannot be 0. L can be 0, M sub L can be 0. So if we know our value for L, let's say L is equal to 1. The way you would figure out the possible M sub L values is we're going to take negative L, so negative 1, through 0, including 0, up through positive L. So the possible M sub L values when L is equal to 1 is negative 1, 0, and plus 1. How do we know that this is a P-shaped orbital if L is equal to 1? Well, that goes back to this important table here. Something to get very familiar with is that when L is equal to 0, we have an S orbital. L is equal to 1, we have a P orbital. Then L is equal to 2, we have a D-shaped orbital. Then L equal to 3, we have an F-shaped orbital. So L equals 0, 1, 2, 3, S, P, D, F. These describe the type of orbital. That means if you know N, you can figure out L. If you know L, you know the type of orbital. Then from L, you can also describe the possible M sub L values. Let's try L equal to 2. It can be negative L, so negative 2. We go up by integral amounts, so negative 2, negative 1, 0, 1, 2. So those are listed here. These are our possible M sub L values. Let's try one more. Let's say L is equal to 3. The possible M sub L values, the possible magnetic quantum number values, negative 3, negative 2, negative 1, 0, 1, 2, 3. So negative L, then integral number amounts through 0, including 0, integral number amounts through positive L. So that was M sub L. Let's go on to the last one now, so M sub S. M sub S is our spin quantum numbers. The possible values for M sub S is only either plus 1/2 or minus 1/2. What does this really mean? Well, for an M sub S of plus 1/2, M sub S of minus 1/2, these are the two possible M sub S values for all electrons. So we can get very specific with our N value, our L value, our M sub L value. When it comes to M sub S, that's always plus 1/2 or minus 1/2. Regardless of what the N, L, and M sub L values are. When an electron is spinning this direction around the atom, this is considered a spin-down electron with a ms value of negative 1/2. I'm not sure why it was showing 2 up arrows. That's another bad typo. This should be spin down when the electron is spinning this direction. Then another unclear typo, I'm sorry about these. I try to catch these images from the publisher. I did not catch this one. When the electron is spinning this direction, it's an upward spin. So spin up is what we say with an ms value of plus 1/2. Then we can also have an electron that is spin down orientation. This is all in reference to how an electron is orbiting around a nucleus and in what direction. So for all quantum numbers N, L, M sub L, the M sub S values show that the electron can either go one direction or the other direction around the nucleus. For M sub S, it can only be either spin up with an ms value of plus 1/2 or spin down with an ms value of minus 1/2. So plus 1/2 spin up, minus 1/2 spin down. Those are only two possible values for m sub s. So we know our possible values for m sub s. To give you a very brief intro to how this was figured out, or a very brief overview, if we have an oven here that contains atoms, if we have an atom beam going this direction through a slit that's in this screen, then it passes through these plates of magnets. Then on this detecting screen, we saw two spots. That denoted a spin down orientation of the electron and spin up based on the orientation or polarity or the positive and negative areas on these magnets. We saw two different spots on this detection screen, again denoting spin down and spin up, or -1/2 and +1/2 respectively. So we went through N, L, M sub L, and M sub S. These are all our quantum numbers that all describe or attempt to describe the location of an electron around an atom, or around a nucleus within the atom. Let's try this practice problem now with that background. So we're going to complete this table by filling in the principal quantum number N and the angular momentum quantum number L for each electron subshell that's listed. So subshell is this combination of this number here and the orbital type here. Going back to this slide, when we looked at N, we saw that this number here describes N. This letter here, these are all the letter S. That must have meant that these were all L equals 0. That letter next to the number of N, that describes the orbital type. When that S is there, that means L is equal to 0. If we see P, L is equal to 1, D, L is equal to 2, F, L is equal to 3. So S, P, D, F, L is equal to 0, 1, 2, 3. So now we can break this down for the number here and then the orbital type here. This is going to tell us our N. This will indirectly tell us the L value. So we talked a bit about N and L. Let's go through more on N and L. So N tells us again how far from the nucleus the electrons in the subshell are. Electrons with a higher N are further away from the nucleus and more likely to participate in chemical reactions. What does this mean? Well, if you remember that sodium can be plus, it can be a cation, that means it lost an electron. The electron that sodium must have lost would have been from the highest N, the highest energy level. That electron that could be plucked away from the sodium atom to become a cation, become an ion, that electron had to be from the highest N energy level. The furthest N from the nucleus, because those electrons here are easier to pluck away and to form a cation in the case of sodium. Once we're starting to draw Lewis dot structures, now we're really getting into what is this idea of a valence electron. The electrons in an atom that have the highest N, the highest energy level, these are called valence electrons. These valence electrons are the electrons in the highest N level. They are furthest from the positively charged nucleus. Electrons being negatively charged, they are held in by the positively charged nucleus. If the electron, however, is further away from that positively charged nucleus, it will be easier to remove from the atom. That positive charge isn't going to be able to hold in that electron as strongly. These electrons here in the inner shells are really hard to remove. These electrons here in higher N values are easier to remove. The ones in the highest N value are called our valence electrons. They're the easiest to remove. Conversely, though, we know that something like chloride will form. That means that an electron was put into the atom. So electrons can be added to an atom or taken away. What we'll get into when we get more into bonding is that atoms are at their happiest when they have a complete octet. This complete octet we'll get a lot more into. It's when they have 8 valence electrons in their outer N shell. Atoms happen to be happiest when they have 8 valence electrons, a complete happy octet. Hydrogen is one exception. It likes to form duets, where a duet is when the atom has 2 valence electrons. Again, we'll talk a lot more about valence electrons. I just wanted to tell you a little bit more because it popped up here. So valence electrons, the electrons in an atom that have the highest N energy level. L tells us how many orbitals are in a subshell. Since each electron orbital can hold only 2 electrons, the number of orbitals in a subshell tells us how many electrons the subshell can hold. So to start getting you used to what these orbitals look like, we have S, P, D, and F orbitals. S looks like a sphere, P, those flower petals, D, even more flower petals, F, even more. Here's even a better look at this. So S orbitals, sphere, P orbitals look like flower petals, D, even more complex, different kinds of flower petals, F, even more complex. These are all lobes or volumes where the electrons could potentially be found. Could be found in this part of the lobe, in this part of the lobe, etc. So each specific orbital can hold 2 electrons. L tells us how many orbitals are in a subshell, where again, each orbital can hold up to 2 electrons. Next, L also tells us the shape of those orbitals in the subshell. So we saw S, P, D, and F all have pretty different kinds of shapes, S being the simplest with just a spherical shape. So the orbital in L equals to 0, remember we're going to say L is equal to 0, 1, 2, 3. Shapes then S, P, D, and F. The orbital in an L equals 0 subshell has the simplest possible shape, a sphere. And orbitals in subshells with a higher L have increasingly complicated shapes, like we saw for P, D, and F. Orbitals with more complicated shapes are not as good at screening outer electrons from the attraction of the nucleus. So less complicated orbital, that positively charged nucleus will be able to more strongly hold on to the negatively charged electrons. But the more complicated the orbital shapes get, the less strongly or the less pull that positively charged nucleus can have on an electron. So in N and L together, this tells us the energy of the electrons in the subshell. This is an important connection here. So N and L together tell us the energy of the electrons in the subshell. Which quantum numbers don't tell us anything about energy? So we don't get anything about the energy from the M sub L and M sub S quantum numbers. Only N and L together tell us about the energy of the electrons in the subshell. Then roughly speaking, the energy increases with both N and L. For example, an electron in the 3D, so 3D subshell, 3, that's our value for N. D right here, let's go up here. D is an L value equal to 2. Right, so D is an L value equal to 2. A 3D subshell, so also the combination of the N and the L, this is the subshell. So a number here and a letter here, that describes what we're calling a subshell. The 3D subshell has a higher energy than an electron in 2p. 2 is our value for n. P here must mean that L is equal to 1. So comparing 3D to 2P, an electron in 3D has a higher energy than an electron in 2P. We could get more precise with the exact energy difference of electrons in different subshells by using this n+1 rule. Again, what are we calling a subshell? It's that combination of n and L. So that subshell is the combination of n and L. We can read n directly from the number that's here. For L, however, we have to look at the letter S, P, D, F. S means the L value is equal to 0, P an L value of 1, D an L value of 2, F an L value of 3. So a subshell we describe as N and L, the number and the letter that we get from here. If you're wondering what happens after L equal to 3, well, that would technically be G would be an L value of 4, H for an L value of 5. However, you don't need to know anything past these because no atoms are yet to be known that have electrons in energy subshells with an L value greater than 3 in their ground state. If you're wondering about ground state, well, this is versus an excited state. So at ground state, the electrons are at a stable state. That's not to say, though, that there are other energy levels that can exist for an atom, and those electrons can go up to these even more excited states, but at their ground state, at their stable state, we don't see electrons in subshells with an L value greater than 3. So if we essentially stop at L equal to 3, what's the max N value we would typically see? Well, to go between N and L, we know all possible values for L are 0 up through N minus 1. All integer values up through N minus 1. So for L equal to 3, the max value for L that we'll see, that's an N value corresponding to 4. So we really don't get higher energy levels for our standard elements above an L value greater than 3. Electrons that are in their stable, non-excited state are called the ground state. We can have electrons that are temporarily excited beyond those energy levels, but in their ground state, this is what we see. So for our problem here, N and L. N we can do without having to do much more, so 2, 4, 3, and 3. For the L, however, we're going to have S, P, D, and F corresponds to 0, 1, 2, and 3. So P means our L value is 1, F means our L value is 3, D means our L value is 2, P again means our L value is 1. So 2, 4, 3, 3, 1, 3, 2, 1 for these different subshells. Right? Subshell again describes the N and the L. These each constitute a subshell. So that was N and L. We'll practice more with N, L, M sub L, and M sub S. So we just focused on N and L. Now let's focus on recognizing S and P orbitals. And they are pretty cool because they do look like balloon animals like we saw. So again, we're trying to describe the possible locations of an electron around the nucleus. When we're attempting to describe the location of electrons around a nucleus, we can actually think about the probability of finding an electron in a certain volume. For example, for a 1s orbital, that is n equal to 1. S means L is equal to 0. S is a spherical shaped orbital. So where 90% of electron density is found for the 1s orbital. 90% of electron density is found in this certain volume for a 1s orbital. As you can imagine, if we start to change the complexity of the shapes of the orbitals, we change the volume that electron could be found in. For a spherical shaped orbital, we can even think of a graph like this, where we have the distance from the nucleus, and then the probability of finding an electron in that certain location from the nucleus. The closer we are to the nucleus, the higher probability of finding an electron for a 1s orbital. Then if we're further from the nucleus, then we have less probability of finding an electron in that location. This is what's known as describing the probability density, or where we might find an electron around the nucleus. So we saw this plot, we talked about that on the last slide. This is known as the radial probability. This is the probability of finding an electron in each thin shell, like n equal to 1, for example. So this radial probability can be plotted versus the distance from the nucleus to give us information about the probability of finding electrons a certain distance away from the nucleus based on the energy level, based on the shape of the orbital. Here again, we have an s orbital. It is spherical. It turns out an electron is most likely to be found at 52.9, what is that again? This is a nanometer. So 52.9 nanometers from the nucleus in a 1s orbital of the hydrogen atom that has only one electron and one proton. Right? Hydrogen has no neutrons. It gets more complicated as we start to introduce more and more electrons to the element. This is just one of our simplest examples, just looking at hydrogen with one electron that is in a 1s orbital. So for L equal to 0, and I really recommend writing this out as many times as you need to. So SPDF 0, 1, 2, 3. When L equals 0, we have an s orbital. Here's some examples of 1s. It's a smaller sphere, 2s, and 3s. So L equals 0, n can equal 1, 2, and 3. What other values could L be if n equals 3, for example, for this 3s subshell? Well, L can equal 0, 1, and 2, right? It has to go from 0 and then integer number up through n minus 1. So for n equal to 3, L can possibly be 0, 1, and 2. For this specific subshell, this is where n is equal to 3 and L is equal to 0. So n equal to 3, L equal to 0 for this specific subshell. When n equals 3, we could also have L equal to 1 or 2. So if n equals 3 and L was equal to 1, we would have a p orbital. If n equals 3 and L were equal to 2, that would be a d orbital. Here, n is equal to 3, L is connected with s, so that is an S-shaped orbital. So it'll be really important to practice if you're given some set value for n, what are the possible values for L, what are the possible values for m sub L and m sub s. M sub s should be clear. It's either plus 1/2 or minus 1/2. Then we just reviewed the possible values for L, then go back and check possible values for m sub L. So you're going to want to get really comfortable figuring out the possible values for these quantum spin numbers. Here now we have n is equal to 2, right, from that 2 out front. Now we have p orbitals. From this graph, when p is here, this is an L equal to 1. All p orbitals come in sets of 3. we can have a 2px orbital, a 2py orbital, and a 2pz orbital, all under the umbrella of n equal to 2 and L equal to 1 for this specific drawing. So all p orbitals come in sets of 3. We can have 2px, 2py, and 2pz that match up with the axes that the orbitals lie upon. 2px on the x-axis, 2py on the y-axis, 2pz on the z-axis. The px, py, and pz orbitals, this is described as these two lobes. Px is two lobes, py is two lobes, pz is also two lobes. The px is one orbital, py is another orbital, and pz is another orbital. So all p orbitals come in sets of 3. So when L is equal to 1, we have p orbitals. In p orbitals, we have 3. Each electron orbital can hold 2 electrons. How many electrons could be found in our 3 p orbitals? In px, that's 2 electrons. Py, that's another 2 electrons. Pz, that's another 2 electrons. In total, the 3 p orbitals can hold up to 6 electrons. For s, that's just one single orbital. So in an s orbital, this can hold up to 2 electrons. So each s orbital can hold 2 electrons. For p, that has 3 orbitals associated with it, px, py, pz. In total, p can hold up to 6 electrons. So let's keep going here and let's try a practice problem to hopefully further solidify these concepts. So are any of these s orbitals? If so, we will list them. Are any of these p orbitals? If so, we will list them. The s orbital has the shape of a sphere. Here's an example of a 1s orbital. The n value here is 1. S means we have an L value of 0. So you should be able to look at a subshell like this and describe the N and the L value. So this is our mathematical sketch of where an electron is usually found in this 1s orbital. It's somewhere inside the space enclosed by the spherical red surface. The electron could be right on the surface, could be even closer to the nucleus here, could be anywhere inside this 1s orbital. And to show these again, this is our x, y, and z axes. So we have 3 axes here. We're used to working with x and y coordinates, but there is a third one we can introduce to have more 3D shaped objects like a sphere and like those p, d, and f orbitals as well. So then for the p orbitals, we know we can have 3 of them. They look like a pair of eggs or flower petals or dumbbells. They can point in the x-axis, in the y-axis, and in the z-axis. So notice this is oriented slightly differently. We've kind of rotated this diagram here. So here's our x-axis, but here's our y-axis. Here's our x, so it's kind of rotated. On the x-axis, we can have the px orbital. On the y-axis, py orbital. On the z-axis, a pz orbital. There's one definition here I do want you to be familiar with. That is a node. A node is a plane in which the probability of finding the electron is exactly 0. So for a px orbital, that has a node in the YZ plane, meaning there is no chance of finding the electron with an x coordinate of exactly 0. So this point right here in the middle of those two flower petals, that's a node. That is where the probability of finding an electron is exactly 0. We're not going to find an electron right there in the middle of those two flower petals. Similarly, for a py orbital, that has a node in the xz plane. For a pz orbital, that has a node in the xy plane, so it's a little bit easier to see here. So that's that node here, where the probability of finding an electron is exactly 0. Well, what about s orbitals? Can we have nodes for s orbitals? Well, no. We don't have any specific parts in the sphere where the probability could be exactly 0. We have no nodes for s orbitals. No nodes for s orbitals. So for a practice problem, are any of these s orbitals? Well, B looks very spherical. Are any of these p orbitals? Well, not this one. This one is not spherical, so this is also not an s orbital. This looks like two flower petals or two dumbbells or two eggs. This is a p orbital. Okay, so again, this one, no, because it's more egg-shaped. S orbitals are spherical. Then for p orbitals, we're only going to have either this kind of orbital, an orbital coming out like this, or an orbital in this plane as well. So x plane, y plane, and z plane, we can find those orbitals. We're not going to see something like this for our p orbitals. So S and then P. So here's our final answer here. Yes, B, yes, A. That was distinguishing S and P orbitals. So next, deducing the allowed quantum numbers of an atomic electron. Here's a nice table summary of the quantum numbers we went through. So N, L, M sub L, and M sub S. We can refer to L quantum number as the angular momentum. So here's what it labels: the 3D shape, the energy level. Remember, N and L together describe the energy. N and L together describe the energy of an electron. To determine the maximum electrons in terms of N, we could use this formula of 2n squared. The maximum electrons in one subshell could be described as 4L plus 2. Here's yet another representation of our spin quantum numbers. Principal, angular momentum, magnetic, and spin. Again, I want you to remember that N and L together, these describe what again? They describe the energy of an electron. Okay, so N and L together, again, describe the energy of the electron, or of an electron. Another table that could be helpful to look at, we have N, L, and M sub L. When N equals 1, L has to be 0, right? L can be 0 up through N minus 1. When N equals to 2, L can be 0 and 1, so 0 and 1. When N equals 3, L can be 0, 1, or 2. Right, so N minus 1, that's 3 minus 1, that's 2. That means L can be 0, 1, or 2, up through N minus 1, which is 2. Then going from L to M sub L can be minus L through 0 through positive L. When L is equal to 0, M sub L can only be 0. When L is equal to 1, M sub L could be minus 1, 0, and 1. So that's seen here as well. What about L is equal to 2? That means it can be minus 2, minus 1, 0, 1, and 2 for our possible values for M sub L. To connect this to the number of orbitals, the way you want to look at the number of orbitals is based on how many possible M sub L values there are. For n equal to 1, L equal to 0, m sub L can only be 0. That's only one possible orbital, so there's one orbital. N equal to 2, L equal to 1 can also be 0. Let's do this case. M sub L can be -1, 0, or 1. That is 3 possible options. The number of orbitals there then is 3. A more complicated one here, let's do L equal to 2. If n is equal to 3, L could be 2. When L is equal to 2, that is a d orbital. For a d orbital, when L is equal to 2, m sub L can be -2, -1, 0, 1, and 2. That is 5 possible number of orbitals. The d orbitals that lead to there being 5, that's this kind, this kind, this kind, this kind, and this kind. That is the 5 different d orbitals. So far, we've been focusing on s and p orbitals, but this is a nice table to help you connect how we get n, l, m sub L, and how that tells us the number of orbitals by looking at the possible m sub L values. Let's try this practice problem of listing all possible values for the magnetic quantum number m sub L for a 1s electron. So magnetic quantum number, that is our possible m sub L values. This 1 out front tells us n is equal to 1. This s here tells us L is equal to 0. Right, so s is when L is equal to 0. M sub L can be -L through 0 through positive L. When L is equal to 0, the only possible m sub L value is just 0. We don't have -0 and +0, so we just have a possible m sub L value of 0. So here we just denoted n equals 1, L equal to 0. The allowed values of m sub L is 2L plus 1. This gives us the integers between -L and +L, so let's practice with the 2L plus 1 for this specific example. 2L plus 1 can also tell us the number of possible m sub L values. Oops, this should be 2L plus 1. If L is equal to 0, 2 times 0 is 0, plus 1, we can have one possible m sub L value. That possible m sub L value is 0. So the number of allowed m sub L values is 2L plus 1, with those integers being between -L and +L. So you can check with this 2L plus 1 and also know that the possible m sub L values are -L through 0 up through +L. Here's this table again, and our final answer then is just a possible value of m sub L equal to 0. This is specifically when we had a 1s electron. So for a 1s electron, this is our final possible value for m sub L. Let's do one more practice with this. So let's do example 7.7. What are the possible allowed values of m sub L when n equals 4 and L equals 1? So we don't actually need to know that n equals 4, right? We just need to know that L is equal to 1. 2L plus 1, how many possible m sub L values could there be? 2 times 1 plus 1. That's 3 possible m sub L values. What are those possible m sub L values? For m sub L, we can go -L through 0 up through +L. Our L value is 1, so we'll do -1, 0, and +1. So this means that m sub L can be -1, 0, or 1. Those are possible values for m sub L given this combination of n and L. We only really need to look at the L is equal to 1. We didn't need to know n to tell us m sub L. N would tell us the possible L values, but not the possible M sub L values directly. Just for a little more practice, if N is equal to 4, what are all the possible values for L? Well, L could be 0 up through N minus 1. That means L could theoretically be 0, 1, 2, and 3. Here we're just focusing on L is equal to 1, N is equal to 4, M sub L could be minus 1, 0, and plus 1. An important check we could do, we know N is equal to 4, but L is equal to 1, S, P, D, F, 0, 1, 2, 3. That means we have a p orbital. 3 possible options for M sub L make sense for a p orbital because we can have px, py, and pz. These M sub L values of minus 1, 0, and plus 1, these all actually correlate to the 3 different p orbitals, px, py, pz. Now, all that we went through here can look really new if you haven't worked with spin quantum numbers before, so don't hesitate to let me know if you have any questions. Definitely work through a lot of practice problems. Just get really used to how we go from N, L to M sub L to M sub S. We'll do more of this in the next part of Chapter 7. So again, let me know if you have any questions. Hope you're all doing well. I will talk to you more for Chapter 7.